Thank you very much for the introduction. It was in 1971 in Mainz at the university when I frequently opened the window and let the radiometer look to the skies. And after about 1 year of measurements in winter and summer, I found the so-called water vapor continuum absorption, which up to this time was only measured in a lab by American colleagues years ago. And then I found its wavelength dependence so interesting that I said we should measure sea surface temperature from space by using two wavelengths in the central window to space, which is from 8 to 13 micrometers wavelengths, and then you could correct the very strong influence of water vapor. When you look from space to the ocean surface, you will never measure the real ocean surface temperature. You measure a mix of emission by water vapor and from the ocean surface, and a bit contamination by carbon dioxide, also some contamination by some acids in the atmosphere. And I propose to do a split window technique. And now we have, since 1981, satellite sensors in space with the so-called split window technique, both in Europe and in the US. It started in the US because Europe was a laggard in Earth observation at these times. We had no real Earth observation capability. What was really done up to this time was having French plans for a geostationary satellite, which later became the famous Meteosat. First series, it went up to number 7, if I remember correctly, all built with technology of the early 70s. And I called them earlier, when I was younger and less polite, UFOs, uncalibrated flying objects. Because Meteosat, old generation, always needed a calibration by some other means, be it vicarious by looking at rather stable surfaces, or being using American satellites. In this case, the famous NOAA series, which is a solar synchronous polar orbiter and not a geostationary satellite. And when you read the title of my talk, Observation of the Changing Earth from Space, this is not my title. It was the title of a brochure of the European Space Agency when rewriting the famous Living Planet report of the mid-90s. And now I'm coming a bit closer to my affiliation with ESA. I started with giving advice to ESA concerning a watercolor sensor and not a sensor for sea surface temperature or other means. Because I had written on behalf of a colleague to the German Ministry for Research and Technology, they should study a system, a push broom technology system. So a possibility to look into one direction, which is space, and the other direction on a detector area is wavelengths. And this should be implemented to measure watercolor from space. Because watercolor from space is the only means to get a global view of the activity of algae. we cannot measure algae directly, but we can measure chlorophyll. And so we proposed in a workshop in 1986 in Ottawa, in Canada, that we should have such a sensor. It was, from the point of view of Germany, the initiation of what later became MERIS, the Medium Resolution Imaging Spectrometer, which is 1/10 of the sensor fleet on Envisat, which is now the sensor used most from all sensors on Envisat, because it has 15 channels in the visible and very near infrared, has a global, comparably high resolution. Every 2 days we get the full Earth's surface with 300 meters resolution. We can look at vegetation, at the height of clouds, at the watercolor anyway, because it was built for this. It was the driver of the sensor, and it is now a multi-purpose instrument, and there is a rotating archive, so you can download it whenever you want it, and you have the means directly, very close to near real time. But when I was studying this water vapor continuum in the early 70s, Earth observation from space was good for calendar sheets and for technology, to drive technology, but the use was far away from what we have nowadays. Nowadays, we have hard numbers. I will show you later, the sea surface height, as introduced earlier at the sidelines, because the talk concentrated on the land surface and water on land. This sea surface observations are so precise nowadays, the height of the sea, that global sea level rise is no longer determined by the gauges. It is measured from space. Every 10 days, roughly, we have a new measurement of the average height of a basin, of all ocean basins you can imagine. We even see that the warm bump, I call it, is going from the northern hemisphere to the southern hemisphere. When we lose the heat in late summer, then the expansion of the upper ocean layers is reduced, and the 2.8 centimeters bump is traveling to the southern hemisphere and coming back next year. So thermal expansion of seawater can be measured from space comparably easily. So we have made tremendous steps forward in the last 10 to 15 years, because earlier it was technology driven more than science driven. Now all the sensors going to space are science driven, at least the ESA sensors. And you have heard that GOES is in space since a few weeks, a bit more than a month. I was involved in stimulating a bit that we get GOES when I was director of the World Climate Research Program in the mid-90s in Geneva, based at the World Meteorological Organization. I wrote a letter to the 5 major space agencies on our globe, and I was asked by the climate research community to write this letter to the space agencies, asking for 5 measurements. Number one in my list was a better geoid. And people were shaking heads. Why are these climatologists asking for a better geoid? We were driven by the better geoid for ocean current determination from space. Because if we know the geoid better, then we can use the altimeter measurements to much better derive ocean current speed at the surface, in the surface layers. Second was the three-dimensional view of water and ice in the atmosphere, liquid water and ice, which was care on the list of ESA. Third was vertical profiles of wind speed, also in the tropics, for weather forecasting, because our ability to forecast weather to the limits and to go into seasonal predictions is hampered by a very meager knowledge of the wind profiles in the lower atmosphere. And we will get AOLOS, or ADM, Atmospheric Dynamics Mission, it was called, but it is a technology driver at the same time, because there is a laser instrument on this sensor which creates sleepless nights for some engineers. It was postponed all the time to launch it, because when we scientists argued for it, it was really at the edge of technological development. And the technological development was nearly too hard. But if you want new observation from space, and you take old technology, then you have nothing new. So it is always a mix between technology-driven new sensors, which give you new observation variables, which really improve the understanding of the Earth. If you just come with old-fashioned radiometers, then the Americans have done it, or even a Brazilian sensor would be in space on this topic. We now have many nations flying optical sensors, as we call them, because it's comparably easy to launch such radiometers. But a laser instrument, or as we heard this morning, a scanning altimeter, this is technology which still does not exist. What you see now is the view of the Intergovernmental Panel on Climate Change concerning the main disturbance on our planet. It is the carbon cycle, which has in the red arrows the anthropogenic disturbance. And I ask you to look at this place here, which is to the astonishment, I hope, of nearly all the teachers here in the room. We have 2,300 gigatons of carbon stored in vegetation, soil, and detritus, mainly in soils. We have added 101 because we fertilize with CO2. What we have brought into the atmosphere is in parts going into the vegetation, and our trees like it because they need a bit less water to produce the same amount of biomass, because the carbon dioxide level is higher in the atmosphere. But because we have destroyed already about 45% of all our forests we had on this globe, we have taken out 140 gigatons of carbon. When you look to the numbers on the arrows, these are gigatons of carbon per year, so fluxes. We emit 6.4 gigatons of carbon per year by burning coal, oil, and gas. The ocean is a comparably lazy deposit. The ocean does not take as much as we would like. Would the ocean mix faster, we had no climate change problem, because the interior of the ocean can take up huge amounts of additional carbon, no problem at all. If we would wait enough now, let's make a Gedanken experiment. We stop emissions today. How much of the surplus in the atmosphere already, though this increase from 280 to 283 parts per million, would go into the ocean? Very close to 85%. So we would lose most of the hangover in the atmosphere into the interior of the ocean. The question is only how fast does carbon go into the interior of the ocean. And if we wait even longer, all would be taken out, because then sedimentation on the ocean floor would bury most of the carbon. If you look to these two arrows here, 2.6 and 1.6, the bigger one says land sink. This is fertilization of all vegetation by higher carbon dioxide levels. It's estimated to eat up 2.6 gigatons of carbon per year, and destruction of forests mainly, politely called land use change, is 1.6 gigatons of carbon per year. There are large error bars on these 1.6 or 2.6, but the sign is correct. So the biosphere on our globe is growing at present and not shrinking. This is not yet in schools, this knowledge. In science, we know it roughly since about 10 years, that there is a rather strong sink in vegetation. Now you have looked at all these numbers here, because I used several minutes for this diagram. You have seen that the rivers bring 0.8 gigatons of carbon per year into the ocean by weathering of soils and rocks. And this is a number we have not changed appreciably. So it is remaining as it was roughly. It's not accelerated, it's not reduced. Now let's look at what Earth observation from space does. Not only give the topic for a lecture in front of teachers, it is detection and exploitation of windows of predictability. All the weather forecasting you get every day, which is marvelous if you understand the language of the meteorologists. It is useful up to 6 days nowadays, so your short holidays you can easily plan by looking at the weather forecasts. In some cases it is going now into weeks and months, in some areas of our globe into a year. The predictability is found for ENSO, for example, El Niño Southern Oscillation phenomenon. But our European Center for Medium Range Weather Forecasting, established in the late 70s, being the best prediction center in the world, is now doing it over weeks and months. You can download from internet the seasonal predictions from the European Center for Medium Range Weather Forecasts. They give it only for those areas on our globe where they find some predictability, because Central Europe, where we are now, is an area with very low predictability on seasonal timescales. But there is good predictability, for example, for Indonesia or for parts of South America, because they are close to the El Niño air-sea interaction phenomenon. Warning of geohazards and mitigation of their impacts. You have seen this morning that frequently services call on ESA and other space agencies, please deliver as fast as possible new images from areas with natural disasters. Control of compliance with international law. The ozone hole, which was not detected by satellites, because NASA, having the satellites at this time of the proper sensitivity, flagged all the observations of the ozone hole because they were so suspicious. They could not believe that this could happen. And so it was ground-based observation of the ozone levels over the Antarctic which detected the hole. But then the size and the changes of the hole are now clearly up to the satellite observations. And there is a lecture here in Vienna these days here where a colleague will talk on the recovery of the ozone hole, or the disappearance of the Antarctic ozone hole, because we have the Montreal Protocol, which was a typical UN-based protocol, nice gatherings, but no hard decisions, until the ozone hole was detected. Then real measures were taken, and now we can look back in Central Europe to 15 years without the production of a single kilogram of CFCs. They were down to zero level in 1994. And in 1985, the ozone hole has been detected by ground-based observations, but in 86, 87, it was clear what the real cause was, the emission of CFCs. Now to Earth observation from space as the backbone of services. I already mentioned it. For weather forecasting, we would be lost in the southern hemisphere completely. I will show you soon a diagram where you see that forecasting of weather is as good in the southern hemisphere as in the northern hemisphere, despite we have nearly no in situ observing system in the southern hemisphere. Nobody is measuring temperature profiles or wind profiles or humidity over the southern Pacific. Only in Australia and New Zealand and in a few islands, sometimes over 3,000 kilometers, no single meteorological measurement. But the forecasts are good in this area. Where does it come from? Naturally, here at this meeting, it must come from the satellites. We have really established services using up to 27 satellite sensors for the starting fields for weather forecasting. The European Center absolutely leading. And now, the number I'm giving you is maybe already too low. 27 different satellite sensors into the starting fields of weather forecasting, updating them twice a day. In build-up phase, it is for oceanography. This discipline is most advanced compared to the others. About 10 years ago, I said agriculture and forestry must get the same services with the same information from space as meteorology, and in the build-up phase now, oceanography. But it is a very difficult task, and Europe is jumping ahead in this. I will show you later. Disaster prevention and mitigation. Chemical weather forecasting. We have now the blueprint for an atmospheric service in Europe where the observations of air pollution will be used for chemical weather forecasting. So forecasting pollution levels or trying to get them reduced, like the European Union does with the directive on aerosols, on these fine particles, to the annoyance of the big cities. Also Vienna struggles with it, because sometimes in our inner cities we have air pollution levels which are too high compared to the standards given by the World Health Organization. This list I took from GCOS. This is the Global Climate Observing System, from their plan of 2004, and read all these variables in green. They can only be taken with space observations. Precipitation. I will show you an example from my own group later, where we measure since 1987 continuously every day precipitation over the ocean. How would you measure precipitation over the ocean by in situ systems? Nearly impossible. If you have 10 rain gauges on a ship, we did it about 35 years ago, then you get, by a factor of 3 differences in the precipitation amount, depending on where you have your gauge, because of the wind strongly affecting what is going into the gauge. Optical sensors are soon, within a few days, without calibration, dead because of the salt in the air. Surface radiation budget. Who measures solar irradiance at the surface? A few highly developed countries. There are only 3 or 4 stations on the entire African continent for the good measurement of surface radiation budgets. I have installed a few of them during my period as the World Climate Research Program Director. And who paid for it? The rich countries, and those giving more to the others than typically the very big ones. You will not find US on this list very high up. It is Canada and Switzerland paying more for such activities. And also Germany was quite low on this list, spending money for the establishment of a better in situ system. Then you have upper air observations, wind speed and direction, water vapor, cloud properties, carbon dioxide, methane, ozone, other long-lived greenhouse gases, aerosol properties. This will never be measured directly from a sounding system with hundreds of sounding stations taking measurements of vertical profiles of carbon dioxide. This will be done from space. But to warn you, it is still not in precision range that you could use it for international law. I estimate that we need about 10 years more to have it in a status where it is useful for the compliance with international law when we have the Copenhagen Protocol, which we will get in December this year, the follow-up to the Kyoto Protocol. So, step by step, Earth observation from space is taking over concerning the observation of our planet. But there will still be plenty to do for in situ systems. Look at the oceanic variables here. Temperature, salinity, current, nutrients, carbon, ocean traces, phytoplankton. You will still need the in situ systems. For phytoplankton, I would green it here nowadays, because Skiamaki, one of the sensors on Envisat, has shown that we can distinguish classes of phytoplankton in certain areas of our ocean system by just taking the high resolution visible radiation backscattered from the ocean surface and from the ocean interior. This is an add-on payload. Skiamaki is on Envisat. It is not an ESA sensor. It has been built by Germany, the Netherlands, and with a small contribution from Belgium. So on these satellites, nations, member nations, or others could add certain sensors if there is space enough and if they do it early enough. This is a promise diagram concerning the weather forecasting capabilities. Here I show the anomaly correlation of the 500 hectopascal height. 500 hectopascal is roughly half of the air pressure compared to the surface pressure. It is at about 5.5 kilometers in the atmosphere. And since we observe directly and from satellite sensors, we can always have, after a few days, the proof of the pudding in meteorology. And then look at the development from of the European Center from 81 to 2006. Would we have an anomaly correlation of 100%, then we have a perfect forecast. 90% is already very, very good. So then the pressure pattern would be very similar already. Your eye would already have problems to distinguish these patterns. And you see in about 2001 or 2, the jump came up to the same precision in the northern and the southern hemisphere. And the southern hemisphere must have, in principle, better weather forecasts. Would we have the same observing system than the northern hemisphere? Because the southern hemisphere has less mountains, less topography. That's why it's easier to forecast developing cyclones or traveling high pressure systems. And day 7 is already a useful forecast. 70% anomaly correlation after 7 days of forecasting time. So try to get to the real information and not to this derivative in newspapers, which has lost most of the information already available from the meteorologists. But as you are teachers, you will anyway go to the internet, I hope, and find the good information and teach your pupils how to find the good information, because in internet about 70% is rubbish. So you have to find the 30%. Now to the promise diagram concerning the freshwater flux. What is freshwater flux? It is precipitation minus evaporation, or evaporation minus precipitation, whatever you define. And let us look at these bands here. This is exactly as we all have learned it, even when you are 69 like me in school. We have the uprising air in the central tropics and a lot of precipitation. So the Hadley cell works in reality. And it was already detected in the 19th century. But you see also where the evaporation sites are. Here, in the subtropics. Most of the water is going into the atmosphere and there is nearly no precipitation. That's why sea surface salinity is very high at these places. So when we would soon measure, when we will soon measure sea surface salinity, then we can make a judgment of this, whether this diagram, it is now a climatological mean. You see averaging from January 1988 to December 2005. And it is not an ESA sensor in this case. It is a military sensor of the United States of America. It's one of the passive microwave radiometers called Special Sensor Microwave Imager, SSMI, which is existing since late 1987, and it's given to the public. And it is now taken on board by NOAA. It's no longer run by the US Navy, but it was a Navy satellite sensor. And you can also see that there is a surplus of water along the Gulf Stream here. This is the area where in October or November more precipitation is dumped into the ocean than in the inner tropics, because the first cold air outbreaks from the inner part of the American continent over the warm water create extreme convection. And when you read ship records, then they will tell you violent snow showers. So a surface temperature of 10, 12 degrees in wintertime, sea surface temperature, and the air coming from the continent in high winter at minus 25 going over this warm ocean surface, then you can imagine how this stimulates convection, and one shower after the other, and snowflakes of more than a €2 coin, also the diameter larger than the €2 coin. Then you can imagine how visibility is going down. Sometimes the ship, the crew even cannot see the front of the ship during such snow showers, and they are nearly every day in this area during this time period. This is a real satellite climatology. We had no possibility for an in situ validation until recently, until one of my co-workers went out to sea into the Nordic seas, into the free Atlantic, and tried to measure precipitation. Because up to this time, we had no observation of precipitation on our globe. And you remember the talk before mine on Africa? No river gauges left, nearly nothing. Despite water is the key substance or the key resource for us, we do not observe it. It is a shame. So we need much more help also from ESA. ESA is now the space agency doing most for the global view, starting global projects which help to understand. I was invited to the wetlands project in roughly 2 years ago. We have a wetland convention, the so-called Ramsar Convention, named after a city in Iran. And it exists since '72. And we still had, 2 years ago, no global wetland map, because the countries don't do it. If ESA would not have stimulated this project, we would have much less knowledge on wetlands on this globe. So we destroy a lot, but we don't care. Monitoring is a buzzword, but it does not happen in most cases. Trend analysis with satellites. So we are already in a position to do a trend analysis, not only, as I've shown, a climatology for Precipitation, it's a mere climatology. There is no trend analysis possible yet because the error bars are still too large to do a trend analysis. You can make a trend analysis only if you have a homogenized series and a strong signal. For the ozone hole, the signal was extremely strong. That's why we have a trend analysis. Having a trend analysis for temperature or precipitation over land, this is a very hard job. You need to remove all changes in the observing system. The rain gauges have changed. Some have windshields, some don't. Some are well run by the service people, but in the meantime, a birch forest grew up near to the station. Then you have a trend of plus 10% in rain, but in reality, there was 0% trend because the wind field was disturbed by the growing forest nearby, and so more, with the higher trees, more of the rain goes into your can. Here we have SST since 1991, 0.13 plus minus 0.03 degrees centigrade per 10 years. This is the observation from a sensor on ESA satellites, but it is a British sensor. AATSR, or earlier ATSR, a long track scanning radiometer. Sea level was shown several times. I will show you a detailed diagram in a few minutes. The intensification of ozone hole until 2006. Now we see no longer a growth of the ozone hole because the CFC concentration went through a maximum a few years ago. And now CFC concentrations, because of the Montreal Protocol, are already declining a bit. And we scientists say there will be an overcompensation because the increasing greenhouse effect will allow the ozone to recover even stronger. So we will have probably more ozone than we had before the ozone hole started, because a cooling takes place. With an increased greenhouse effect, the surface warms, but the upper layers in the atmosphere, roughly starting at about 15 to 18 kilometers upwards, cool. The cooling of the stratosphere at present is much stronger than the warming at the surface. So this anthropogenic influence is easily detected in the higher atmosphere. Nitrogen dioxide, plus 50% over China from 1995 to about 2 years ago. When you have very strong signals, then you can make a trend analysis. If you have a 10% economic growth, like China had, averaged over a decade, and you have an energy input also of 8 to 10%, and you do not have directives to reduce pollution, then NO2 must grow with 8 or 10% per year as well, and it did. You can smell it when you travel to China. As I could smell it when I traveled to East Germany, when we still had the German Democratic Republic, you could smell all the air pollution. This country was overwhelmed with pollution. You could smell SO2, and you could smell in summertime NO2. Cloud albedo has been reduced, so our clouds are now darker than they have been because of the Gorbachev effect. Because the collapse of the Soviet Union created a strong reduction in emissions of SO2. So less particles, and the water in clouds is then on larger cloud droplets, and the brilliance of clouds when looked from above is depending on the sum of the cross sections. And if you have more particles and the same amount of liquid water, then the clouds look more brilliant. Or it is a paradox for laymen. The more polluted an atmosphere, the more brilliant the clouds developing in this polluted atmosphere when looked from above. If you are at the surface, they are darker. Then you have less solar radiation reaching the surface. This is a diagram I took from one of the publications of ESA, The Changing Earth, published in 2006 by the Earth Science Advisory Committee of ESA, where I was a member of until 2006 or 7. I do not remember exactly. I wanted to step down because younger should do it. You see from 1992 onwards until, in this case, only to 2006, the different sensors used to establish sea level rise. And you see the yearly cycle, which has not been removed in this diagram I mentioned before, because of the different size of the water surfaces in the northern hemisphere versus the southern hemisphere, and a stronger heating of the northern hemisphere summer, we have a yearly cycle in average sea level. And you see how well the different sensors fit. And it was not the big pencil used. It was a combination of different publications. Sometimes we have an idea in our head, and then our fingers follow the idea, and a bit less the points measured, which is illegal in science, but it sometimes happens. Now to the cloud reflectance over Europe. What is shown here is how much in thousands the albedo was reduced when the clouds had an albedo 60 to 62 or 68 to 70%, which is already a very high albedo, 68 to 70%. These are brilliant clouds. In maximum, they can go up to 80% reflection and not more. And the same is here for the summer period, and this is for the winter period. There is a clear tendency that these darker clouds, even where a lot of soot was also involved, went up in albedo after the collapse of the Soviet Union, and when the Western countries had Clean Air Acts. They also contributed to this recovery of the clouds. And now to the ships. We can even observe that our European harbors are the most polluted areas nowadays. While over Europe, the reflectivity or the albedo of the clouds shrank, it grew over all harbor areas, because this is the only emitter which is nearly unregulated. They burn all the remnants from our refineries in gasoline and in diesel. No sulfur is any longer allowed, but so-called Schweröl, heavy oil, burnt by ships, has all the remnants from the refineries. Or you can speak of waste incineration on sea. And the International Maritime Organization has started with regulations, but when you go with a ship across the Atlantic, you can still burn this waste. And that's why we have here on this diagram an increase in cloud albedo and a decrease in cloud top temperature. Strange enough, if you have a very polluted atmosphere, the clouds, if they develop, shoot up higher, because the polluted atmosphere suppresses drizzle formation, which starts in clouds. And if you have more liquid water per volume, and these clouds freeze at minus 15 or minus 20 degrees centigrade, then more heat is released during the freezing process, and then they shoot up a bit higher. This can all be seen by satellites. We would never have had money enough for airplane experiments to derive such a diagram. In this case, it is NOAA satellites. It's the advanced, very high resolution radiometer of an American satellite series for meteorology. This I jump over because it was shown already by others. Now to the sun. There is a big debate even here again whether the sun does it, the global warming or not. And this is the observation of the output of the sun over the last nearly 3 cycles of the sun. And up and down, but it is only about 1 per mil. And again, a paradoxical situation. The sun is, on average, brightest with a lot of spots, which is against physics if you do not look more carefully into the system, because the dark spots on the sun indicate here is less emission. Why should a sun with a lot of spots have a higher emission? Because the areas around the spots, larger areas, are more brilliant. So we have 0.1% or 1 per mil up and down in the 11-year cycle. And there is no trend visible for the sun in the recent nearly 30 years. Challenges to be answered soon. As a scientist, I am always looking ahead, and we debate uncertainties. We love to debate uncertainties and not to give what we know. But it is wrong in the public. I have worked in the public now for 30 years, and I know you should start with all what we know, instead of immediately jumping into the areas we don't know. Sources and sink distribution of carbon monoxide, methane, and carbon dioxide by inverse modeling using data from Envisat and METO. We will never be able to measure nice profiles in the next 10 to 15 years. All we have is column contents. Then we bring these column contents into a circulation model of the atmosphere, and it should tell us where are the sources and sinks which can explain the observed pattern of column contents. This is so-called inverse modeling. It's very advanced. In the meantime, there are large groups doing it. Trends of cloudiness by better intercalibration of satellite series. We have no idea whether the clouds get more frequent or less, because the group which has done it for the World Climate Research Program has to struggle with intercalibration, because up to now it was not the task of the space agencies to carefully intercalibrate from one sensor to the next. It is now done in parts, so it is seen as a task, and in GMES it is written into the files that it should be done by the space agencies and not by others. Homogenization of time series is a very difficult task. The single time series of Hohenpeißenberg, the oldest direct observing station in Germany, and I think also in Europe, because they measure since 1783 or 4, continuous observations every day. And recently, the former head of the observatory found out that all the old numbers are wrong, because the glass used for the first thermometers was a glass which shrank during its lifetime. And so the scale was wrong. And this takes about 0.4 degrees centigrade. If you correct it now, then the so-called very warm years at the end of the 18th century become much colder, and the present period is a real hot one. And this is due to shrinking of glass, which was produced in the 18th century in a very famous glass factory at this time, but they were not as good as glass factories nowadays. Phytoplankton time series through combination of these sensors I have listed here, because we have no idea. Does phytoplankton production increase or decrease on global scale? Or in other words, is the fertilization effect of higher carbon dioxide levels in the atmosphere, which also translates into higher concentration in the surface layers of the ocean in parts, is this stimulating phytoplankton growth? But then you need the fertilizers. Are they enough to push? And how many percent of what is produced in the surface layers is eaten up by zooplankton immediately and does not settle into the ocean? Is there a carbon sink or none? This is still an open debate in science. Did Earth observation influence international law? I already said yes for the Montreal Protocol, no doubt. Yes, in parts for EU climate policy, if EU Council decisions of March 2007 are implemented. They are binding, but still not implemented. For the first time, we have a mass flux reduction as a binding goal for Europe. Minus 20% for CO2, and 20% of the end energy used in Europe must come from renewables in 2020. These are binding goals of the European Council. A population has not realized it yet. And I look at your faces and then I realize you are belonging to the normal population. Hopefully for the follow-up to the Kyoto Protocol. And do we have, this is my last slide, do we have a balanced European system of Earth observation? Normally scientists will say, no, we need this and that, as I wrote in this famous letter in 1996 to the space agencies. We have the Earth Explorer Core and Opportunity missions, run by the Earth Observation Envelope Program of ESA. If we would stop this, then everything dries out. Then our standard sensors would soon be close to rubbish, because no progress. If you have an operational satellite system, you need always an infusion from science. Always, every few years, you must have better algorithms. You must replace sensors by new ones. This is sometimes very costly, but the return is high. Operational meteorological satellites built by ESA, but run by EUMETSAT for improved weather forecasts, and they deliver fundamental data for the global monitoring for environment and security services. This is in very good shape in Europe. METOP and Meteosat second generation are the best operational meteorological satellites at present in space. Sentinelle de la Terre, GMES operational satellite series. The name is from a former director of Earth observation of ESA, and he is a Frenchman, so we call it Sentinels in English, but his famous book, Sentinelle de la Terre, has stimulated the debate. And we will have new operational services within GMES as part of the global Earth observation system of systems, which was pushed by George W. Bush when he realized the Europeans want GMES, then we have to make it global, because without leadership, the Americans cannot do anything. Thank you.